Okay, good morning everyone. Can you all hear me?
Yes, good morning.
Morning. Okay, so yesterday we were discussing, where did we stop yesterday? We stopped at the point where I had given you a question to think about, right? So the question to think about was if you have a flow in a network N, right? So let's say the flow is F, then under what circumstances can you obtain a flow of value greater than F, right? So you want to get a new flow, F prime. Okay, so the new flow is F prime, and we want the value of F prime to be greater than the value of F. Right? So when can we do this? And before we go to this question, we discussed an important proposition, or I guess I called it a theorem, which is that for any flow and any cut, F and K respectively, the value of the flow is less than equal to the capacity of the cut, right? In particular, if you have a maximum flow F and a minimum cut K, then the value of F has to be less than equal to the capacity of K, right? Okay, so today we will discuss the max flow min cut theorem, which actually says that this is not just a less than equal to, it's actually an equal to, right? But before we get there, let us think about the following question, because the proof is going to be an algorithmic proof. Okay? Um, yeah, as I said, there are generally two sides to anything. There is an algorithmic side, because most proofs are constructive, and then there is a more proof side of things, but they're just two sides of the same coin, right? Okay, so they're going to go hand in hand. So before we state the Maxwell-Minkert theorem, let's think about the question that we had posed in context of this network. So here you have a network N, and you have a flow in green color, which is slightly different from the flow I was using in previous examples. And what I want to do is, I want to obtain a flow which is better than this one. Actually, let's call this flow F1 rather than F. Okay. So this is the flow F1, and we want to now get a better flow, let's say F2. And the question is, how do we do it? Okay. So take a close look at this example. And what is a simple way? You don't even need to tell me in this example. In general, for a network N and flow F1, how will you get a better flow F2? What is a very simple idea? I don't want a complex idea. I want a very simple idea. Anyone
Fine.
who has not seen the topic in the past, maybe? Let's see if anybody has any ideas. Anyone who has not seen this topic in the past? I'll give you a hint. Think of a directed path from S to T. Right? And the hint is, think of a directed path from S to T. Okay. If not, then well, anybody else can respond.
We find a directed rough from S to T such that the capacity of those edges is not full yet.
Right, right. So this is a very straightforward idea. So the first idea is to find a ST die path, let's say P, such that for each arc in P, the flow on the arc F1 is strictly less than the capacity on that arc. Okay? Supposing we can find such an ST die path, then we can easily uh, get a better flow. Okay? And let's see. Can we find such a ST die path in this graph? Can you look at the green numbers, which are the flow F1, and find an ST die path where the flow on each arc is strictly less than the capacity on that arc?
SP3 V40.
Right. So let us look at this path. So I'll just mark it. Going from S to V3 to V4 to T. Right? Notice that 1 is less than 4, 0 is less than 1, and 1 is less than 4. Right? And so what would we do in this case? I'm going to call out someone. Pawan, are you there? Hi, Pawan. So what should we do in this case? You can type. You can type if you prefer. Since there is a lot of background noise at your end, you can type. So we have an ST die path, S to V3 to V4 to T. So how can we get a better flow using this ST die path? Right? So we have this path S, V3, V4, and T. And we want to get a better flow using this die path. And I will write down the better flow here. Okay, anyone else? So presumably you don't want to make any changes to the arcs that are not on this die path, right? I mean, that seems to be clear. So let me put down those numbers. In the meanwhile, I would like someone to tell me what I can do on that ST die path.
Send a flow of 1.
Send a flow of 1. You mean increase by 1 on each arc?
Yes, yes.
Okay, great. So let's see if I have marked everything else. Yes. Oh, I think I still need to mark one more. This is 0. So what you're saying is, because the flow is less than the capacity, and in this particular case, the difference between the flow and the capacity is at least 1, right? Here it is 3, here it is 1, and here it is 3. So what we can do is we can increment by 1 on each arc, and we will still have a flow, right? So I'm going to make this 2, I'm going to make this 1, and I'm going to make this 2, right? So the changes are just in these places, right? Good. So whenever you find an ST die path with this situation, what you can do is you can look at the minimum of the difference between CA and F1A for each arc on the path P. Okay, I'm viewing P as a set of arcs, right? What you can do is you can take the minimum, let's say this is epsilon, and now what you can do is you can obtain a new flow F2 by keeping the same flow on all other arcs. So F2 is going to be F2 of an arc A is going to be the same as F1A if A is not in P, and if it is on P, then I'm just going to add epsilon to it. Okay? So epsilon is the minimum of this quantity, right? And in our example, epsilon for this path, the green colored path, is equal to 1 because it is a minimum of 3, 1, and 3. Okay? And you can convince yourself quite easily. Convince yourself that F2 is a flow in N. Okay? So can someone else tell me what you need to prove, what you need to do in order to prove that F2 is a flow? What are the things you need to check to prove that F2 is a flow?
Capacity and conservation constraints.
Exactly. You want to check the capacity and the conservation constraints, right? So the capacity constraints are going to be met because we chose a path where F1A was less than C of A for every arc, right? The flow was less than the capacity for each arc. And we are increasing by this quantity. And so you can see that it will still be less than the capacity for each arc. Okay? And for the conservation constraints, it's actually quite straightforward because what we did is we just took a directed path from S to T and we increased the value by epsilon on all of these arcs. Right? And so for each vertex, for each intermediate vertex, if you increase by epsilon on an incoming arc, you also increase by epsilon on an outgoing arc. Right? And if a vertex is not on the path, then well, nothing has changed. So it doesn't matter. Right? Okay. So the flow on the incoming arcs is still going to be equal to the flow on the outgoing arcs. Are there any questions regarding this first idea? Because after this idea, it turns out that this idea is not going to work always, and we need a more sophisticated idea. So if there are any questions right now, then just ask them before we move on to the more sophisticated idea. No? Is everything clear? Okay. All right. In that case, what we now have is, let's call this the red colored flow. This is the flow F2. Okay. Good. So this is the flow F2. And now, what do we think? Can we again find an ST path? Can we again find an ST die path where each arc has flow strictly less than the capacity? Can anybody find such a path? It's a small graph. Take some time and let me know what you think. In the meanwhile, I'm going to make a copy of this drawing. So I'm going to make a copy here. Let's see if we have enough space. Okay, that should be fine. And I can erase some things. Okay, so we have the flow F2 in the same network as before, right? The network never changes, of course. And now I want you to tell me, can you find an ST dipath where the flow is less than the capacity on every single arc? Anyone?
I think
No? I didn't hear you.
There does not exist a path.
There does not exist such a dipath. Okay. Does this mean that this is a maximum flow just because there is no such dipath? Or is there something we can still do to get a better flow in this example? So the
If we
answer to this is
reduce the
no.
flow on
Sorry?
some of the edges, if we reduce the flow on some of the edges, we can still obtain a better.
I see. I see. So, second idea. Sorry, my phone is trying to answer the question I'm asking. Okay. Second idea. Could we? I mean, this is counterintuitive, right? It seems a little bit counterintuitive. Could we reduce the flow on some arcs? Could we reduce the flow on some arcs and perhaps also increase the flow? Well, to get a better flow, right? So I'm using the term flow with different meanings here. By here, this term I mean the F value on a certain arc, right? And when I say flow, actually what I mean is a ST flow, right? Anyways, you get the point. To get a better flow, right? So here I actually mean the F value for some arcs. Okay, so can we try to formalize this further? How would we do this? So Ritvik is suggesting that we can reduce the flow on some arcs. Okay, how do we choose such arcs? So previously we were using the notion of an ST dipath. What should we do now? Any ideas? Let me give you a simple example. Supposing I find a path like this, okay? And let's say the flow here is 1, the capacity is 4, the flow here is 1, the capacity is 3, and the flow here is, let's say, 1, and the capacity is again 4. And there is a whole network. I'm not drawing the whole network, right? I'm just drawing one path. It's not a dipath anymore. What can I do in this example? What can I do in this particular example? Any suggestions? So there are other arcs coming in here, okay? Don't worry about that. Okay, so what do we do in this particular example to get a better flow? We want to just make changes to these three numbers, 1, 1, and 1. We are not going to make changes to anything else in the network, in the any other flow values on the network, right? F values. So how can we modify these ones and get a better flow in this particular small abstract example? Any ideas?
If we reduce the flow which is going out of like the second last vertex, like
Okay,
1 comma 3, then we can increase
okay,
the flow 2t, like it could be 2 comma 4 towards t.
right, okay. So what we are suggesting is increase this 1 to 2, decrease this 1 to 0,
Yeah,
and increase this 1 to 2,
yeah.
right? And this works because you see what are the things you have to check. Well, the capacity constraints are clear. I am respecting them. Some one of the numbers has become 0, but that is not a problem, right? But let's look at the conservation constraints. If you look at this vertex, we have increased the flow, incoming flow by 1, and we have sorry, right, we have increased the incoming flow by 1 on this arc, and we have also decreased the incoming flow by 1 on this arc, right? So the incoming flow has been decreased. It has been increased by 1 and decreased by 1, so it is still 0, and the outgoing flow has not changed at all. If you look at this intermediate vertex, what has happened is the outgoing flow has reduced by 1 and the outgoing flow has increased by 1. And so again, the outgoing flow has not changed, the incoming flow has also not changed. Is that clear? Right? And this turns out to be the correct idea. Rather than looking at ST die paths, what we are going to look at is ST paths in the underlying undirected graph. So basically what you do is you forget about the directions, you just find a path in the undirected graph that satisfies certain conditions. And that turns out to be the correct idea. Okay? So instead of finding an ST die path, we are going to find an ST path, right? So we don't care about the directions, but we will care about the directions when we consider the conditions satisfied by the arcs. Okay. So the second idea is to find an ST path. Ignore the directions. Okay. We'll find an ST path P that satisfies the following conditions. Okay, so although we are looking at an undirected path, we are still going to call it an ST path, okay? Because we want to view that path as being traversed from S to T, okay? So let me just make a drawing. So we are looking at a path that could look like this, for example. But we are still going to think of the path as if we are going from S to T, okay? We are traversing the path but the path itself is not a directed path. And what we will do is we will call arcs going like this as forward arcs, and we will call arcs going like this as reverse arcs. Okay? So this is a forward arc, this is a forward arc, this is a forward arc, and this is a forward arc. Okay? and the remaining are reverse arcs. Okay, reverse, reverse. Okay, and what we want is, look at this example again. What we did is we increase the flow on every forward arc and we decrease the flow on every reverse arc. Okay, when can we increase the flow? When it is less than the capacity. When the F is less than the capacity, you can increase it. When can you reduce the F? Well, it has to be greater than 0 because we are looking at non-negative function, right? So if it is already 0, then you cannot decrease it anymore. But if it is positive, like in this example, then you can decrease it to 0. Okay? So the conditions we want are that for every forward arc in P, we want the flow of the arc to be less than the capacity of that arc. And for every reverse arc, we want the flow value, the F value, to be greater than 0. Okay? And now let's go back to this example. Can you find a path like this in this graph? Is there such an ST path here? Is anyone able to find such an ST path in this graph? Of course, we have not studied any algorithm to find such a path, but that's a secondary matter for now. Right?
S, V3, V2, V1, V4, V.
Thank you. That looks to be correct. So let us look at this path. I'll color it in blue. From S to V3 to V2 to V1, you said?
Yes.
Oh, but using this arc,
Yes, yes, yes.
like the reverse arc.
Yes, yes.
Okay. Then I go to V4
Yes.
and then I go to T. Okay. Let's see. So here the flow on the first arc SV3, the flow is less than the capacity and it is a forward arc. The second arc V3 to V2 is also a forward arc and the flow is less than the capacity. Now we are taking this reverse arc from V2 to V1. Okay. And because this is a reverse arc, we don't need the flow to be less than the capacity. We just need the flow to be greater than 0. Okay. And now from V1 to V4, this is a forward arc again. The flow is less than capacity. And V4 to V4 to T, it's the flow is again less than capacity. It is a forward arc. Okay. So what we can do is we can increase the flow on each forward arc and decrease the flow on each reverse arc, right? And then we should be able to get a better flow. So let us just try doing this. I will write down the new flow in a blue color on the same directed graph, right? I won't make a new copy. So how much can we increase and decrease by? That is a big question. How much can we increase or decrease by?
1.
1. Why? Why can't I do 2?
You have the edge with which has just one flow, right? Which you want to
Right.
reduce.
If you look at this number here, it is 1. The best you can do is you can reduce it to 0. But that means that you can also not change other numbers by more than 1. So what we'll do is we will add 1 for all the forward arcs and we will subtract 1 for all the reverse arcs. Okay? So this becomes a 3. This becomes a 2. This one becomes a 0, this one becomes a 2, and this 2 becomes a 3. Okay? All the other numbers are as they were before. Okay? So for all the other arcs, the red value is the same as the blue value. The red, yeah. The new flow is the same as the previous one. Okay? And now you can check that this is actually a flow. And you can prove it actually easily based on the kind of arguments we used here. Okay? Look at each intermediate vertex and think about what happens at that intermediate vertex. Okay? Either you will be increasing the incoming flow and the outgoing flow by an equal number, or both of them will be unchanged. Okay? Good. So let us, are there any questions on this new idea? Is it clear why this works?
Yes, it's clear.
Yeah? Okay. So, well, I will write down a proposition. In the meanwhile, if there are any questions, just feel free to ask. Okay. So, I just want to make it very clear what we are doing here. So, the proposition, what we just sort of discussed, and you can prove it on your own rigorously. I won't spend time on proving it rigorously, but we have essentially discussed all the important points to prove it. So, let F denote an ST flow in a network N, D with source S and target T and capacity function C. If there exists, oh, I should give this a definition. Such a path is called an F incrementing ST path. Okay? So it is a path going from S to T, not a directed path, a path in the undirected graph. But when you view it from S to T, all the forward arcs have flow less than the capacity, F less than C, and all the reverse arcs have F greater than 0. Okay? If there exists an F incrementing ST path, say P, then we can get a new flow it is going to be a new flow, so it is going to be a function from the arcs to the reals, non-negative reals, defined as, so what we are going to do is, for every arc that is not on the path, we are going to keep the same flow, right? We are going to keep the same F value. If A is a forward arc, right, then we are going to add epsilon to it. Okay, we need to define what epsilon is. And if it is a reverse arc, then we need to subtract epsilon from it, right? The question is, what is epsilon? We will discuss this. So the proposition as stated is incomplete. What we want is, we want this to be an ST flow, and what will happen is that the value of the flow will become the value of F plus epsilon. Okay? Good. And this means, in particular, this means that F is not a maximum flow, right? Because you're able to find a better flow. Okay, so the only thing that remains to discuss is what is epsilon? How do we choose epsilon? So in this example, you chose epsilon to be 1, right? How do we in general choose epsilon? Anyone? Anyone else? So of course we can choose epsilon to be a very small number, that is fine. What I want to do is I want to choose epsilon to be as big as possible while still making sure that we have a flow, right? I mean, I can choose epsilon to be a very small number and that gives me a bigger flow. But I really want to choose it to be as big as possible so that the algorithm runs fast. That's the idea. How do we choose epsilon? How did you choose epsilon in this example?
Forward consider CA minus FA, for backward consider FA. Take a max over all this.
Take
Min
the
overall.
what? Take the
Take the
minimum.
min overall. Yes.
Right, right. So remember, for the forward arcs, we know that f of a is less than c of a. So the best we can do is we can increase it by c of a minus f of a for the forward arcs. For the reverse arcs, the flow is f of a, and what you can do is you can decrease it to 0, right? So the best you can do is reduce it all the way to 0, right? And so what you need to do is you need to choose the minimum of all these numbers. Because if you choose a bigger number than the minimum, then one of the constraints is going to be violated. One of the, either the capacity is going to be violated or you are going to get a negative real number, and that is not allowed because we are working with non-negative real numbers. Okay? So what we can do is we can write it in the following way. We can take it as the minimum of epsilon 1 and epsilon 2, where epsilon 1 is the minimum of FA minus CA. Am I doing this right? CA minus FA, sorry. For each arc, that is a forward arc of P. A is a forward arc of P. I don't like to use the symbol A because it's very confusing with the article A. But anyways, it's too late now. And epsilon 2 is the minimum of FA, where A is a reverse arc of P. Okay? So in this particular example, what you would have done is you would have taken the minimum of 2 because 4 minus 2 is 2. 2 again, and here also it is 2, and 2 here as well. And then epsilon 2 is going to be the minimum of 1. And so the minimum of those two is 1, right? And that is why we chose epsilon to be 1. Okay? So in this proposition,
Sorry.
we,
Again,
yes,
how we are determining this?
right. So let us look at this arc. Let us look at this path again. I'm just going to make the drawing of the path here. S to V3. Then we are going to V2. Then V1 is going into V2. So the arc is going in the reverse direction. And then V1 is going to V4. And then V4 to T. Okay, you agree that this is the path we found?
Yes, yes.
Okay. So now what we are going to do is for the forward arcs, subtract the capacity, subtract the flow, the red number from the capacity, right? So 4 minus 2 is 2. Then 3 minus 1 is 2. For the reverse arcs, we are going to take the flow value. So that is 1. Okay. That is this one here, the red number. Then again we have forward arcs. So 3 minus 1 is 2 and 4 minus 2 is 2. Okay. So epsilon 1 is the minimum of these four numbers. I'm sorry, the example is not too interesting. So it's just the equal to 2. And epsilon 2 is the minimum of all the reverse arc numbers, right? And epsilon is the minimum of epsilon 1 and epsilon 2. Is it clear how we are determining,
Yes, yes,
right?
yes.
And hopefully it's also clear why we are making this choice. Remember that we have to respect the capacity constraints. So we cannot
Yes,
increase the flow by more than this value on the forward arcs. And on the reverse arcs, we know that we have to keep the numbers to be non-negative. So if the flow is 5, you cannot reduce by 6 because then you will have a flow of minus 1, right? So if the flow is equal to 1, then you cannot reduce by more than 1, right? Is that clear?
yes, yes.
Okay, good. So this proposition is correct so long as you also include the definition of epsilon, right? So where epsilon is chosen as this quantity, and now what is true is that the new flow you will get will be, I mean, the new f prime you will get will also be a flow. Okay. And well, we have essentially proved the statement, except that I have not written down rigorously or in complete detail, step by step. So the proof is left as an exercise. But everything that is required for the proof has already been discussed in this lecture. Okay. So the main point is, the summary is that if there exists an f incrementing ST path, then f is not a maximum SP flow, right? This is the main point. And then there are lots of details. Now, whenever you see a statement like this, a very natural question arises. What is the natural question that arises? Can someone tell me? What is the immediate question that arises when you read this statement?
If f does not have an incrementing path, then is it a max flow?
Exactly. Is the converse true? Is the converse true? In other words, if there does not exist an f incrementing ST path, then is f a maximum ST flow? What do people think? What do folks think? Well, no guesses?
It should be if and only if, like,
Yeah,
the reverse
right.
should also be true.
So, in fact, that is right. Yes. And what we will do, so I want you all to try to prove it yourself. Okay. You can take an example and work out some examples and see if you can get some ideas on your own. Um, you might have to consider a slight generalization of this notion. Rather than looking at ST paths, you might have to look at paths starting from S and not necessarily ending at the vertex T. Okay. Um, but more importantly, what I want you to do is think of the following question. If there does not exist an F incrementing ST path, then can you find a cut? Can you find a cut K partial plus of X, right? I should say ST die cut. Can you find an ST die cut such that the capacity of the cut is equal to the value of the flow? We will discuss this tomorrow. But before that, supposing you can find such a cut, then what does it mean? Can someone tell me? Supposing you can find a cut, ST die cut, whose capacity is equal to the flow, then what does it mean?
Then K is a minimum die cut and F is a maximum flow.
Exactly. If this is true, then by the previous lecture, what we discussed, then by the theorem in the last lecture, K is a min cut, a minimum ST die cut, and F is a max flow, a maximum ST flow. Okay? And so think about, take some example, maybe the example we already did. I have a feeling that now after this new flow, there might not be any F incrementing ST die paths, F incrementing ST paths. I'm not sure. I will have to inspect this example more closely. But the more important question is, if you can't find such an ST path, then how would you find an ST die cut that has the same capacity as the value of the flow? Because if you can find such an ST die cut, then you will know that the flow is a maximum flow and the cut is a minimum cut. Okay? And that is actually the content of the max flow min cut theorem. Okay? All right, so this is the end of today's lecture and we will continue tomorrow. But if there are any questions, please stay back. And I'm here for another 10-15 minutes. All right, Govind, what did I want to discuss? Can you remind me? Oh, I see. Yeah, I am going to discuss this in the next lecture because students have already started leaving, and I still need to think about it myself. Okay, thanks. Probably I'll put up an announcement to discuss the matter, and then we will discuss in the next lecture.
So this is an administrative question, but are you taking attendance?
Um, well, we are keeping track of who's attending, and that's about all the information I will disclose.
Huh, okay.
There are no marks associated with it, if that's what you're asking. We're just keeping track to make sure that everybody is with the course and following the course, and nobody is, especially in this time of a pandemic, I want to make sure that everybody is keeping up with the course and not just drifting away. So that is the intention with which we are keeping track of attendance. Any other questions?
Thanks a lot.
Thank you. You're welcome. Okay, so Pappu has a question. Why did we not increase the forward arc by 2? Right. Okay. So let's, you mean in the example, right? Right. Okay, so let's see what happens if we increase the forward arc by 2. Okay. So supposing, okay, so let me just look at this. Notice that we have a path like this, right? Something like this. Okay. Supposing we increase the forward arcs all by 2. Okay, because epsilon 1 was 2 and epsilon 2 was 1. And let's say I decrease this by 1. What do you think is the problem now? Remember, we had a flow, and what we have done is we have incremented the f value on each forward arc on this ST path by 2, and on the reverse arc, we have decreased by 1. So now, if you look at this drawing, just this particular drawing, then what do you think is the problem? Do you think there is any problem, Papu? Or do you think everything is okay? Papu, can you hear me? Okay, so is the new function f prime a flow? Supposing we have f, and now after increasing and decreasing, we get a new function f prime. Is f prime a flow? An ST flow? What do you think, Papu? Is the new function a flow? Okay.
Hello.
Okay. Yes, yes. So you think this is a flow?
Yeah.
Okay. Okay. What are the conditions for a flow? Let us go through them together. What are the conditions for a flow? What are the things I need to check to confirm whether a given function is a flow or not?
Is the
I can't hear. Maybe you have to type again. Papu, can you hear me? Capacity. Okay, so capacity constraints. And what else is the condition for a flow? Apart from capacity, what else do we need to check? Yes, conservation. Right. So the other thing you have to check is the conservation constraints. Right? So which one you think is a problem? Is either of them a problem here? Let's check capacity. So for each of the forward arcs, you are increasing by a number which is epsilon 1, right? Which is equal to the minimum of capacity minus the flow, where A is a forward arc. Right? Okay. So this is fine, right? Because, sorry,
Okay.
this is fine, right? This is not a problem. What? Or there is one more condition which is a bit we don't generally state it. There's another condition which is non-negativity. You agree? But this is generally stated in the definition.
Actually, I want the reverse is decreased by 1 and the forward
Yes.
is increased by.
Yes. So I want to
Why?
understand which of these three goes wrong. There is one of these three which is not going to be one of these three constraints. One of capacity, conservation, and non-negativity will be violated. Which one is it? So capacity is not going to be violated because you're only increasing by epsilon 1. Non-negativity is also not violated because you have reduced by epsilon 2, and that is also fine. What about the conservation constraints? Will the conservation constraints be violated or will it not be violated?
I think it is not good.
Not violated? Okay. Think about this vertex here. Papu, think about this vertex. Okay. What happens at this vertex? What happens to the incoming flow? Supposing this is the vertex V. I want you to think about how has the incoming flow changed at V and how has the outgoing flow changed at V.
Okay, got it, got it.
Yeah, you agree
Okay.
that this is violated. So the
Yeah.
conservation constraints are violated, and that is why it is important that you increase or decrease by the same number on all the arcs of the path. And that is why you have to take epsilon to be the minimum of epsilon 1 and epsilon 2. Okay?
Okay, okay.
Good, good. All right. Any other questions? Well, if there are no more questions, then you may proceed to exit the lecture. And I'll have just short discussion with the TAs. Anand, are you there? Okay, I'll remove you from the meeting. Hi, Govind and Shantini, are you there?
Nishad, you're still recording.
Sorry, I didn't hear you.
You're still recording.
Oh, I'm still recording. Sorry. Thanks.